It's another fairly simple example. This time it's a cantilever. We've got a 3 kilonewton point load, 4 meters from the support. Maybe the whole thing's 5 meters long. Should probably just put that on actually. We'll just stick that on. So just make this 1 meter from the end or something like that. Because you want to draw the shear force diagram over the whole length of this thing. So first thing is always to draw a free body diagram, and then we're going to find the reactions. So I'll work through that and I'll see you on the other side. I might stop a little bit just to explain how we're getting the reactions, just so you don't forget, but I'll see you on the other side. Okay, so just find the reactions the normal way. So here you're just putting these on whichever way you think they should go. Rather than doing positive and negative just in the answer, I'm just drawing the direction they're going in. But I could put positive and negative. This would be positive. This one would also be positive, which is what we're getting. I haven't drawn on my axes. I should have really done that just to show where I'm taking my axes from. So this is going to be Y, and in this direction is going to be X. And now we want to draw the shear force diagram. So again, I'll just draw a few different sections just to illustrate this one more time, why it's the case that you get a constant shear force. But after that, we can probably just use the little trick we learned in terms of when you're drawing the shear force diagram, you just kind of follow the forces, stay constant in between, follow the force. Sounds a bit like a Star Wars movie, but you're following the forces to draw the shear force diagram. But I'll draw a couple of sections first, just to show you why that's true. And so if we were finding the internal forces, we'd just be drawing sections along this. So I might do one at 2 meters and one at 3 meters, something like that. And you can get to see what's happening. Okay, so I've drawn those two sections. I'll just leave this one empty just so you can see which end's being cut at. So it's, oops, wrong one. Just fill in this end as well with a thick line. So I'm just cutting it here and thinking about the left-hand side, and then I'm cutting it at 3 meters and thinking about the left-hand side, so that's 3 meters. Lazy about my line types, but anyway, my 3s are a bit rubbish. I've realised from the fact that when you're doing the tutorials, you sometimes think they're a 5. It looks like a 3 to me. So, what would you do if you're trying to find the internal forces at that point? So just the same as what we did before, we'd be thinking about what is positive shear and positive moment. Well, positive shear is like this. You've got up, left, down, right. And so we are on the right-hand side of this section. And so we'd want to be going down the way for the shear. And so we draw on the shear force that we've made external by splitting it, would have been there. And then for moments, sagging is positive. That is one of the worst drawings I've ever seen. And so you'd have to be going like this and like that to bend it in that shape. And so on the right-hand side, it's going anti-clockwise. And so you'd be drawing it on like that. And you get the same thing down the bottom here. So let me just transfer those down. So that's just for the next section along at 3 meters. This would be MA, but we're not really thinking about that yet at the moment. Diagram, we'll get to the bending moment diagram next. We're just thinking about the shear at the moment. The shear at the moment. Anyway, just thinking about the shear. And so I might just take that off. So at the moment, we're just thinking about shear. We're not worried about that moment yet. So we would have found that that's the only time you use these is when you're drawing on these fake external forces where you've cut it. So the only time you use this as positive. You now switch back to the usual positives. And so if we were to calculate, we would be trying to calculate that shear. We'd just be using sum of the y components equals 0 to do that. So sum of the y components equals 0. That means 3. And then VA is down the way, so minus VA equals 0. That means VA is equal to 3. So the shear at A is equal to 3. And it's down on this side. If this had come out, anyway, we won't go through that again. If it had come out negative, it would have been the other way, which would have been a negative shear. Negative shear is like that, where you're going up on the right-hand side, blah, blah, blah. Now, so that's that one. And then for this one, nothing changes in this equation. Just because you've moved a bit further along, it doesn't change this. None of it changes. It's all still true. The sum of the y components is equal to 0. Therefore, VA is still 3. And so what we're seeing here is that that shear force, so the internal shear force, it doesn't change unless there's some kind of force there. Could be a line load, we'll get to that shortly. But unless there's a force in between, it's not going to change. Now, we should have really done one at the end here. So give me 2 seconds to draw that. So what I've done now is I've drawn it as if I've gone just a little bit past this 3 kilonewtons, so 4 plus a little bit. So we've just gone a little bit past that 3 kilonewtons. So it's now coming into the diagram, and we've got VA. We'd also have a moment, but we're not worrying about that at the moment. So what would we have this time? Well, we'd have the sum, Fy0 still. Then we'd have this up 3, so plus 3. And then we'd have a minus 3. Then we'd have a minus VA, all equals 0. And so what is VA? Well, VA is just equal to 0 kilonewtons. Each of these should be in kilonewtons. Shear force is in kilonewtons. And so what does that mean? Well, it means that you come along, so you start off, it's going to be 3 kilonewtons all the way along here. So 3 kilonewtons all the way along here. You get to that 3 kilonewtons, it drops to 0. So it's going down 3 kilonewtons, and then it'd be 0 for the rest. So if we were going to draw the shear force diagram, we just draw some axes first. And how long are we? 1, 2, 5. 1, 2, 3, 4, 5. We'd have this one is going to be the shear in this direction. And we're going up to 3, so let's just draw it like that. And this is y. This is x. And so we can use the rule we learned about before. This first part, we've got a force going up 3 kilonewtons. We figured out that reaction was 3 kilonewtons. So our shear force diagram is going to go up 3 kilonewtons. Then it's just going to keep going flat until it gets to the next point. And the next point is the next load, sorry, or the next point load. And then it's going to go along 4 meters, and then it's going to reach this 3 kilonewtons. It's saying go down 3 kilonewtons. So that's exactly what the shear force diagram is going to do. It's going to go down 3 kilonewtons, and then it's going to be 0 until the end of the beam, because again, there's no forces. So for point loads, for getting a shear force diagram with point loads, it's really quite easy. You just go up by whatever the point load is, continue along flat till you get to the next point load, go down. And if you had multiple point loads, that would still be true. And so this would be, I should really put on what this is. Now I did y there, but it's not. That's V, the shear. X is okay. This would be in meters. This would be in kilonewtons. And you could shade that. And so usually you just do that as a hatch pattern. So shaded it just makes it easier to see where it is in these graphs. That's about it. So let me just see here, just a second, just tidying that up. So we could have gone straight to this as soon as we'd figured out the reactions, to be honest. And so you're just starting at this end, you know the reaction's going up 3 kilonewtons, you go up 3 kilonewtons, you keep flat until you got to the force, and then you go back down again. But keep in mind, you have to understand where that's coming from. And so you have to understand this stuff, otherwise you can tie yourself up in knots. That's that one. Let's have a look at